Hello, testing. Hey everyone, my name's Max. I'm here to talk to you about recent work titled Full Swap Regret and Discretized Calibration. This is joint work with these lovely people right here. For the purpose of this talk, I want to talk about the problem of calibration. It's this classic problem in online learning, and it falls under the umbrella of a more general framework that is the focus of this paper called Full Swap Regret Minimization. The purpose of the paper is to come up with general algorithms for everything in this framework that captures algorithms for calibration, also some new problems, exciting stuff. But, let's focus on calibration for now. Let's define calibration, all right? So the setting of calibration, the selection of the umbrella on the previous slide was no coincidence. Let's talk about rain for a second. Let's imagine that you're a weather person and you're repeatedly tasked with predicting whether or not it's going to rain, okay? So each day, you come up with some forecast and then observe if it rains or not. So, formally, you make your prediction, you realize some binary outcome, and you repeat. The next day, you make a new forecast, realize some binary outcome. Cool. We do this for capital T days. And your goal as a forecaster is to be calibrated, meaning that if you look back on all the days you predicted 20%, it empirically rained on about 20% of those days. If you look back at all the days you predicted 30%, it empirically rained on about 30% of those days. And the goal is to accomplish this calibrated forecasting even when this binary outcome is selected adversarially. Someone's trying to mess with you, you're still trying to be calibrated. Okay, let's add a little complexity to the picture. If you're predicting your forecasts deterministically, the adversary can just mess with you. If you're going over 50%, they'll make it sunny. If they're going under, they'll make it rain. So really, this forecaster is predicting a distribution over forecasts. Okay, that would be the more formal way to state it. So exactly, for every single day T, you produce a distribution over forecasts. The adversary then selects a binary outcome. For each prediction, you could then, at the end of time, look at what's the empirical frequency on those days, weighted by how much you predicted that forecast on each day. And then you define your L2 calibration error to be essentially summing over, the possible predictions of the squared error between, your forecast and the empirical frequency, weighted by how much you predicted that one thing. I'm doing a summation here, not an integral. You can think of X as like finitely supported. There's some finitely distributed forecast distribution. Cool, that's L2 calibration. So let me introduce just quickly a related notion of calibration, just to talk about some past work. You do L1 calibration. That's the same thing, but it's the absolute difference rather than the squared difference. Cool. 1998, these guys Foster and Vora, they cook up a sublinear L1 calibration algorithm. That means that you can literally just stay inside all day, not look at the clouds, and be a good calibrated forecaster over a long enough time horizon, even when an adversary is choosing the weather to try to mess with you. Crazy result. Another recent paper between myself and some other collaborators, we shaved like a 1 over 1,000 off the exponent. Incredible research. This paper for L2 calibration, we're getting a t to the 1/3 rate for this different measure of calibration. This is, I guess, no longer the best known rate. I guess, it's not explicitly stated anywhere. The reduction that we do in this paper can also be used for L2 calibration. You can shave your 1 over 1,000. But the thing about this work is we're actually achieving this calibration algorithm in a very principled way. And it ties to this kind of classic connection between calibration and what is known as swap regret minimization. Also, this problem is like a very large part of my life still. I'm trying to get an even better algorithm, and I guess the current approaches all involve this connection to swap regret as opposed to the crazy reductions of this other work. So this is a peer into my life more in terms of what I'm working on. So cool, let's define what swap regret is. Let's talk about online learning in general. So in general, online learning, you have some set of actions, and you're going to repeatedly choose an action. So at every single time step, you make a choice, and then incur some loss, as well as observe the loss of all the actions you didn't choose. And you repeat. You try to adapt to the losses you're seeing, make good selections. Similarly to calibration, you're allowed to select a distribution over actions. You get an expected loss. Okay? So formally, make this distribution. Adversary chooses the loss. There's the total loss. The performance measure here is regret. There's many different types of regret. Let me start by defining it in a general abstract, and then we'll go through maybe more familiar specific notions. Regret is always going to be a comparison between the total loss you got versus some sort of benchmark. So, we do some online learning task, we're making selections, receiving loss, get some total loss. And what we're going to consider is some sort of transformation fee that we're going to take this ledger of everything that's happened during this online learning and transform all of the actions according to this transformation and look at this transformed loss, okay? So in the most general, we define fee regret, capital fee regret, to be some sort of set of transformations, and we want our total loss to be comparable to all the transformed losses. Okay, that's the very general definition. For external regret, which is the classic, we are setting our capital fee to be the set of all constant maps, right? So we're competing with the transformations that map all our actions to some sort of best fixed action in hindsight. That's the definition that's most common, external regret. There's also this thing called swap regret, okay? And swap regret entails competing with all possible maps from the set of actions to themselves. What that would look like is, maybe you did some online learning. Some rounds you went with action A, some rounds you went with action B. What we're competing with here is taking each individual action and swapping it for its own best fixed action in hindsight. For all the rounds you played A, what's the best round fixed action there? And okay, again, we're dealing with like you're allowed to do distributions over actions, so that would accordingly map the component of each distribution to, what we're swapping it for. So this is similar to calibration. Cool. And that's how you define swap regret. Wonderful. So how can you view calibration as swap regret? There's this kind of classic connection that's been observed by, I learned this in your textbook, man, so thank you. It was very useful. Cool. So calibration, let's remind the setting. So we are selecting, distributions over forecasts. The adversary is selecting these binary outcomes. And so we're actually going to be able to map this to a swap regret instance. So what we're going to think of is, instead of this guy choosing this binary outcome, they're going to choose, a loss function. That's either going to be, x squared or 1 minus x squared, based on the binary outcome. And actually, swap regret here corresponds to L2 calibration. So what would swap regret be? It would be, summing over the predictions of, the loss contribution from that prediction compared to what's the best thing we could have predicted in space of that probability. What is that best swap for probability P? It's exactly the empirical frequency from before, right? The mean is what's going to minimize squared error. Cool. So you plug that in. You do your difference of squares factorization. These guys are equal. Mathematics. L2 calibration. All right, cool. So why am I calling this full swap regret as opposed to regular swap regret? It's just to disambiguate the following. I guess typically you're thinking of a discrete action set when you're doing swap regret. So your selection of a distribution over actions is corresponded to the selection of a deterministic point in some sort of convex set, which is the simplex. Here, the action set is a convex set. So my distribution over actions is a distribution over points in a convex set. And here, like all functions from end to end would correspond to all the linear transformations from this set to itself. Here I'm talking about all the maps from this set to itself. Linear, nonlinear, discontinuous, all these things. So I just use the phrase full swap regret here to distinguish when we're talking about these convex action sets. All right, cool. So we've got a swap regret minimization problem, right? We have this action set that is the interval. We're receiving these, parabolic losses. All right, let's just minimize swap regret, right? This is this, notion that's been studied before. It corresponds to, learning in games. If you're using swap regret minimization, you get these nice stability points. So let's just use one of these pre-existing algorithms, right? There's the Bloom-Mansour algorithm, which guarantees a swap regret rate that is, square root of time and also the number of actions. All right, well, I guess we have an infinite number of actions, so we gotta mix things up a little bit. You know, I guess the classic idea would be to discretize, right? You know, we chop up our infinite interval into, you know, like n discrete actions, and, you know, we convert our loss function to a loss vector that is just what is this function evaluated at all these points. Cool, you plug this into Bloom-Mansour. You get a term coming from the, you know, the rounding that you do. You get a term coming from Bloom-Mansour. You balance, you get t to the 3/5. That's good. But, you know, we kind of lost something here. We lost something because we had this nice, strongly convex loss, you know? And we turned it into a loss vector, which is not going to immediately give us any improved rate. So one of the key ideas of this framework is essentially the following. Opening the black box of Bloom-Mansour a little bit, you know, essentially how it works is you instantiate a copy of an external regret algorithm for every single action. So that would be like the recommendation of algorithm A. You stack them up into a matrix, which gives you a Markov chain, and what you actually play is going to be the stationary distribution of this Markov chain. Don't worry about it. You then input back. Okay, so you know what we did on the previous slide would entail, you know, coming up with an algorithm for each of the discretized points. Each of those algorithms outputs to the discretized values. You're getting this 3/5. But the idea, I guess, of this, one of the key ideas of this paper is that, you know, indeed, we're going to produce an external regret algorithm for each action in the discretization, but we're going to have those algorithms output to the continuous real line from 0 to 1, right? So each of these is going to be an instance of like a convex optimization, like OCO, so we can still use that strongly convex loss, but even though we have discrete, finitely many algorithms. You then round those to get your Markov chain. Okay, that's the idea. All right, you know, you're holding on to the structure of that convex, strongly convex loss, which gives you this kind of log t instead of the something square root of t. You get your t to the 1/3. All right, we can explain that more offline. So yeah, our main results in general are, you know, you have some sort of convex action set in d dimensions. You have these Lipschitz loss functions, and you know, for various assumptions about, you know, the structure of your loss, whether they're strongly convex, smooth, you get all these different full swap regret rates. You know, again, you know, d we're imagining here to be some sort of constant. You know, it's like an infinite action set, but if there's some sort of constant dimensional structural assumption that you have, you get these sublinear rates. If I have any more time, I'll just quickly mention discretized calibration. This is a cool application of our, of our full swap regret framework. You know, we've been talking about how you can take a full, like a continuous algorithm and like kind of do a discretization. Sometimes it's actually useful to take a discrete instance of swap regret and map it to something full. You get an improved rate. So, you know, we gave you this algorithm for calibration. So, you know, you go get a job as a weatherman. You start predicting, probabilities that are multiples of 1 over the cube root of time. You get fired immediately. They're like, what are you doing? You know, they expect you to kind of already go with their pre-described discretization. They want you to, you know, output multiples of 5%. So what that would look like is, you know, what I'm saying is my action set is already discretized. And, you know, my calibration error is already only comparing to this discrete set, right? So, you know, that would correspond to like just this finite action swap regret instance that we described previously, right? This is literally just a finite action swap regret problem. You could just apply Bloom-Mansour. But actually, you get an improved rate by taking this already finite thing and turning it into this infinite continuous thing. By essentially, you know, like essentially what you're going to do is I'm going to replace my action set with, you know, the actual full interval. I am going to, you know, replace this loss vector with this, you know, piecewise linearization. And then I'm going to run full swap regret minimization on this, and then round it back to the discrete set. And if you do this, you actually get this an improvement, you know, and it indeed makes sense that it's actually something, you know, you get a better rate as n increases, right? As n gets larger, you know, and this thing becomes more smooth, we should get a better rate, not a worse rate. We're getting more strong convexity. The key here is this, like, you know, subroutine that involves like just external regret minimization over piecewise linear functions. That's another cool thing that we develop in this work. All right, that's it. Thanks for watching.
Yeah, so your last thing here, when you ended up with your piecewise linear function instead, why not try to I mean, to not make it piecewise linear and just like get a good old polynomial stuff instead.
Yeah. So I guess this represents. So again, like if my continuous algorithm output this action, what we would then do, because we have to play from this distributions over this discrete set, you would represent it as a mixture of the two neighbors, right? And so like this linear component between these 2 points would actually like represent exactly the loss you would get as, so like everything in this little interval, you'd be playing some sort of mixture of these two guys. And that would mean it's like this linear function. So we don't really have a choice in the fact that this is piecewise linear, but there's these interesting things that we can do when we have this function that is, because right, this isn't strongly convex, right? We can't just out of the box get the improved rates from a strongly convex function, but in some sense at a large enough scale, things do kind of like curve upward. So it's this kind of balance of, locally you get only the convex guarantee, globally you get strongly convex, you can get improved rates. Yeah, I was happy to discuss more.
Connection between swap regret and calibration for squared loss was not known before? Or?
No, so the connection was known. I guess the idea is like that, like rather than, we have this discretization, but having the specific external regret algorithms like playing back in the continuous setting, right? So rather than a discrete set of algorithms playing over a discrete action set, you do this discrete set of algorithms, but then going back to this continuous action set, you can take advantage of the structure of your loss function.
I see, okay.
Yeah.
So maybe let's take one more question later, Max, and the rest offline.
Yeah, just a very basic question. Do you have a feeling what the correct asymptotic dependence is for like d equals 1? I mean, I think you said at some point that you can actually do better than a third generically, right?
Man,
so what's the right answer, you think?
I guess it's somewhere between like 1/3 minus 1,000, and I think 0.08 would I guess be the lower bound from that other paper. I think it's t to the 1/5. Some of the people I work with think it's t to the 1/4. Maybe it's some crazy log. Who knows?
Okay, maybe I'll ask you for intuition
Yeah,
in the break.
that out in short order. All right, everyone. Thanks. There. Yeah.